Hi guys, it's nice to be back again with you all with econometrics this time. So before we move on with the subject and start off with econometrics, I have a small request to be put forward from my end. Okay, so that's a very small favor. Before we start off with econometrics, I want you all to have a clear understanding of what and how regression works, especially the initial parts where we went through how we derived the population regression function, the sample regression and like that's very important. So I want you all to refresh that memory. So pause the video now itself. If you all have forgotten, if you all think you all have forgotten, pause the video. I have attached the link of the relevant content in the description. So I have mentioned the timings as well. Look into that and come back again. And now you all will have a clear understanding and better grasp of knowledge when it comes to econometrics. Okay. So yes, let's dive into this. The first concepts which we have to cover is where we talk about the three concepts like independence, mean independence, and uncorrelatedness. Okay, now if you all remember, in correlation we had this part saying correlation takes values from -1 to +1. Yes, when it's -1 we say the two variables, let's say the x and y variables, they are perfectly correlated, perfectly positively correlated. And if it's -1 we said it's perfectly negatively correlated. Yes, negatively correlated. And if it's closer to +1 we say it's strong over here, and if it's over here we say it's weakly positively correlated. Likewise, when it's over here we say strongly negatively correlated, and when it lies somewhere over here we say strongly negatively, weakly negatively correlated. Yes, now if r is equal to 0, how did we interpret this? You might say no correlation, but actually there are two parts under this. We can say x and y variables are independent. Okay, so here we give the interpretation as independent. That means they are not correlated at all. There is no relationship between them. Another way of interpreting r equals 0 is where we say there is no linear relationship. You all might remember that in correlation we particularly talk about only linear relationships. We never touch non-linear relationships. So when r equals 0, it can give us two outcomes. It can either be those two are correlated. Actually in the real world, in real scenario, there is a relationship between them, but it is not a linear relationship. Or when r equals 0, we can interpret saying actually in the real world there is no relationship at all, meaning they are two independent variables. So this is where we start off our discussion about independence, mean independence, and uncorrelatedness. No relationship at all, right? So this is that independence concept. When we say no linear relationship, that means it's referring to non-linear relationships. So this is what we refer to as uncorrelatedness. Remember in stat 1, we learned that in probabilities, probability of A intersection B, which I can write as A comma because intersection is multiplication, right? Probability of A intersection B is probability of A into probability of B when A and B are independent. Yes. Likewise, over here, when two variables are independent, we can say that their joint distribution, that is joint distribution, we show it as function of x comma y, is equal to the product of their individual functions. So individual function of x is function of x and of y is function of y. So we can say that the joint distribution of x and y, this is, you mention it as joint distribution function of x and y is equal to the product of their marginal distribution function. So here we have the marginal distribution function of x. Of x into marginal distribution function of y. Okay, so hereby we can say that x is independent of y. Likewise, the converse is also true. Y is independent of x, which we can write it as function of function of y comma x is equal to function of y into function of x. So since this works both ways, we can say that the concept of independence is symmetric. Now, when we move on to mean independence, you all will have a clear and better understanding of what this symmetric is. The next part is mean independence. Here we are also gonna apply the same approach which we used in probability. So when two sets were independent, we said that the probability of given probability of A given B is equal to probability of A. How did we get this? Because probability of A given B, we can write this as probability of A intersection probability of B divided by the probability of B. Okay, so we know that probability of A intersection B, when they are independent, we can write it as like this. Yes, so here I can write probability of A into probability of B divided by probability of B. So now we can cut these two and this will come as probability of A. So that is how I got this. Likewise, here in mean independence, what we are saying is the expectation of y given x is equal to the expectation of y. Now this is why I asked you all to refer to the how we derived population regression function, all those parts, because in regression, how do we get the population regression function? First we set the values of x. Okay, if I use the same example as I used in that previous video, just a quick refresh of memory. So I had used, I think, x as income. So I had given different levels of income, 100, 150, 200, likewise. Now what we did was, now if we want to get the consumption expenditure of people who have earned an income of 100,000, I went and surveyed families of five odd families and got the information of their consumption expenditure. So this was income. Then we took 5 families. This is their consumption expenditure. Then I collected 5 samples, right? So these are the details of the 5 sampled families. Then I went to 5 families who are earning an income of 150,000 and noted down their consumption expenditure. Likewise, I went to 5 families who are earning 200,000 as income and wrote down their consumption expenditure. Okay, so let me jot down some values. 85, 80, 90, 92. Okay, then 200,000 also, let's say 60, 70, 75, 100, 105. Likewise. So when I am going to form the population regression function, what I did was I calculated the average of all this. So I added all this and got the average. Okay, then I got all this and got the average, and got all this and got the average. That is how I derive the population regression function. So to give a basic idea, so this is 100, this is the 150 level of income and 200 level of income. These are the 5 sample points which I've got. Okay, these averages over here, that comes like somewhere here, and then I form my population regression function. So if you see my x values, that is the income levels, I have fixed it before conducting the survey itself. Before conducting the sample survey, I have fixed my consumption levels, x values. After I fixed my consumption values only, I went to the experimental sample and collected the relevant information, which is non-random. So when we do like that, when our x values are fixed, the expectation of y, that is the mean value of the y variable, is equal to itself, that is mean independence. So if I am supposed to give it in text, I mean like a definition or something, we can say mean of a variable, mean of a variable is not affected by another variable. Okay, here you see mean of y is not affected by x when they are mean independent, when y and x are mean independent. Regardless of the value x takes, the mean of y is the same. Let me repeat that again. Regardless of the value x takes, it can be 100, 150, 200, whatever, the mean of y is the same. Okay, so since I've written like this, this can be interpreted as y is mean independent of x. So here we have the conditional mean of y given x. What is the condition? We have already set the values of x. Conditional mean of y given x is equal to the unconditional mean of y. Now if I write the other way, that is expectation of x given y is equal to, what can I say? When the y values are fixed, the mean value of x is the same, right? So that's equal to expectation of x. So how do I write down this in words? X is mean independent of x. Okay, that means the conditional mean of x given y is equal to the unconditional mean of x. Alright. So, but the thing which you'll have to remember over here, the most important factor is, since expectation of y, that is this part over here, let me highlight and show. Since this is true, we can never say that this is also true. Now, if you see in independence, we said that when function of, when this is true, automatically this is also true. And that's why we refer to this concept as symmetric. But in mean independence, just because the first part is satisfied, that doesn't mean the second part is satisfied. We have to again do the proofs and see whether it gets satisfied. So because of that, we call this concept as not symmetric. Alright guys, if you all prove this, that doesn't mean this gets true. You have to again prove and see whether that is true or not. Alright, next let's move to uncorrelatedness. Uncorrelatedness is very simple. So when we say uncorrelated, that means the correlation is equal to 0. Okay, that is where we specifically refer to lack of linear relationship. R is equal to 0, right? So if you all remember the formula for correlation, we wrote it as x minus x bar, y minus y bar divided by x minus x bar square, y minus y bar square. So basically, what does this mean? It's the covariance of x and y, divided by the standard deviation of x and the standard deviation of y. Okay, so in order to say that two variables are uncorrelated, that means r equals 0, if we can just prove that the covariance is equal to 0, we don't need to prove actually. When we say that covariance of x and y is equal to 0, that automatically means the correlation is also equal to 0. Therefore, both are uncorrelated. So if you refer to the slide, under uncorrelatedness, there is this specific thing they have written like this. When two variables are uncorrelated, expectation of xy is equal to expectation of x and expectation of y. Now, how did we land over here? That is something which we have to look into. So now, like I told before, correlation is the covariance divided by the standard deviation of x and y. So if we all remember the formula for covariance, how do we write covariance of x and y is equal to x minus x bar, y minus y bar divided by, depends. If you are finding sample covariance, you divide it by n minus 1. If it's population, n. So I'm just writing n. Okay. This, when you are writing in population characteristics, okay, covariance of x and y, if you are writing in population characteristics, there are certain notations which you all have to use. So x bars over here, x bars will become mu x. Same, right? X bar is for sample. Usually we use it for sample. Mu x in population terms. Okay. Likewise, mu y bar will become mu y. So this is x minus mu x. This is y minus mu y. Okay. We take the summation of that. Yes. How did we do? We take the summation of that and divide it by the number of observations. So this is basically, this is how you find mean. Mean, expectation, both concepts are the same. So I am going to write over here expectation. This is how you convert and write. Now, this is not actually conversion. This is, I'm simply writing in population terms. Okay. Now what I'm going to do is I'm going to cross multiply these values. This with this, this with this, this with this, sorry, this with this and this with this. So what you get over there, expectation will remain outside. X, Y, first term. Then is X into mu Y. So I am writing it as mu Y into X. Same. Then minus mu X into Y. Yes. So minus mu X into Y. And next is minus mu X into minus mu Y, which is minus into minus is plus. Yes. So I am writing it as plus mu X mu Y. Okay. So here this expectation factor should be applied to each of these parts. So it becomes expectation of xy minus expectation of mu yx minus expectation of mu xy plus expectation of mu x mu y. So this will be remain as expectation of xy. We know that expectation, that is mean of a constant, is the constant itself. So if you note, mu y is a population parameter, that means it's a constant. Likewise, mu x is a population parameter, constant. Mu x into mu y, this is also a population parameter, so constant. So that means we can take it out. So I can write this as mu y expectation of x. Likewise, mu x expectation of y. Here I can simply write it as mu x mu y. Okay. Now you all know that expectation of x is actually what? I can write it as mu x. Okay. Likewise, over here, expectation of y, I can write it as mu y. I hope you all got that. Expectation of x became mu x and expectation of y became mu y. And I write the rest like as it is, mu x mu y. Now if you all notice, here we have minus mu x mu y, here we have plus mu x mu y, which can be cut. So what do we end up with? Expectation of xy minus mu y mu x. So I can write this again as expectation of xy minus expectation of x into expectation of y. Yes, mu y is expectation of x, mu x is expectation of, I think I have switched it up, guys. Sorry. So both are the same anyways. Mu y is expectation of y and mu x is expectation of x. Okay. So covariance of x and y is equal to expectation of xy minus expectation of x into expectation of y. Okay. So since x and y are uncorrelated, we said that covariance of x comma y. Where did we say? When we prove that this part is equal to 0, it means it's uncorrelated. Yes. So we know that because both these are independent and uncorrelated, covariance of x comma y is equal to 0. So if this part of the function of the formula is equal to 0, I can bring this onto this side basically, and I can write it as expectation of xy is equal to the expectation of x into expectation of y. Okay, so this condition over here, this doesn't happen always, not always, guys. Okay, this is only true when x and y are uncorrelated, only true when they are uncorrelated. All right, so what we mean by uncorrelatedness, this is, you all have to remember, it refers to lack of linear relationships. So uncorrelatedness doesn't mean x and y are independent. That for that we have a specific concept called independence. If two variables x and y are uncorrelated, it doesn't mean that they are independent necessarily. What they are referring to as a lack of linear relationship is that these two variables have a non-linear relationship. So when we look into the three concepts, that is independence, mean independence, and uncorrelatedness, we say that independence is a very strong concept. That is because if two variables are independent, that means necessarily it is mean independent, and therefore it is uncorrelated as well. But the converse is not true. That means if two variables, if they are uncorrelated, that doesn't mean that they are mean independent, and that doesn't mean it's independent. This doesn't work, but the other side works. Okay, if they are independent, it implies that it's mean independence and it's uncorrelated. So when you come from top to bottom, it's correct, but you can't go from bottom to top. That part you have to remember. So if you look into the slides, there's a question they're asking, which of the following is true? So y'all can do that and check whether y'all have understood the concepts or not. Okay.